So hi everyone, I'm Pietro and welcome to my session where I present you Custom Processing Unit. So first a few words about me, but you don't see the slides. I see them there. Okay, so a few words about me. I'm used to say, hey, I'm a PhD student, but this is no more true since I defended it 2 days ago, so this is pretty full week for me. So I'll just say you, I'm a researcher, very interested in low-level research, very low level, as you will see. And okay, I spoke a few times at Black Hat, got 2 Pony Awards with my research, and one of them was for the most innovative research for an initial version of this talk. So you will see the new version, actually. So what can you expect from today? We will have a full deep dive into CPU microcode, to the deepest level of our CPUs, of Intel CPUs. I'll present you the first framework for microcode reverse engineering and customization from the software level, so without needing any external hardware debugger. And I'll show you how you can use our framework for CPU customization, like for adding important security features or even improve the performance of Intel CPUs. We will also use the framework to reverse engineer the secret microcode update algorithm, which, okay, now is no more secret, but you will see. So first of all, a disclaimer. Okay, this whole work is based on our understanding of CPU microcode. So okay, in theory, all of the talk could be completely wrong, but in practice, you will see that a lot seems right since stuff is working, actually. So we have to first understand how do modern CPUs work. And with a very, very high level and wrong, probably simply overview of CPUs, we can think about CPUs like it being divided with a front end and a back end. So the front end is the component that is responsible for fetching the instruction from memory, decode them, and pass them to the back end. And the back end, or out-of-order execution engine, will just execute those microoperations. But I told you a very specific word that should not make sense, that the front end is supposed to decode operations. And why is that? The issue is that the fact that x86 instructions are a complex instruction set architecture is basically just a lie. The backend will not be able to execute complex instruction, but will only be able to execute very, very simple instructions, these so-called microoperations. So what the front end will do is to decode those microoperations, those instructions into microoperations that can actually be executed by the backend. So okay, most instruction will be decoded into 1 to 4 microoperations. Think about if you have instruction that access memory or do simple arithmetic computations. But there are a few instructions that model very, very complex functionality. For example, think about CPU ID, where you may have different functionalities depending on the input data. And those instructions will have hundreds or even thousands of microoperations to implement the microcode routines that will actually implement the semantics of those instructions. And those instructions are the so-called microcoded instruction. So as every time for research, we build our research on the shoulder of giants. And we start our work from the work of Mark Ermolov and his colleagues, where they, exploiting the CPU, or in particular Intel Atom Goldman CPUs, they were able to achieve the read and lock of those CPUs. Read and lock is a very interesting and particular state of CPUs, where you basically are able to debug and access the internal buffers of the CPU using an external debugger. Using our read and lock CPUs, they extracted and reverse engineered the format of Goldman microcode. And while reverse engineering that format, they discovered a few undocumented instructions that are able to access internal buffers from the software of the CPU. So our whole talk starts with the question, what can you do with the access of microarchitectural buffers? We will start from a post-exploitation stage to understand what can we do to a CPU. And the answer is bad things and good things. But to understand what can we do, we have to understand, okay, how do microcoded instructions work? And we can imagine that there is some sort of translation or lookup table inside the CPU, where every time you are about to execute an instruction that is microcoded, this lookup table will bring the execution to the so-called microcode ROM that actually holds the microoperations that implement the microcode routine required to implement the operations for example, CPU ID instructions. As the name says, this microcode ROM will be immutable. So you will have no way to update the microcode if, for example, you discover as a silicon producer that there is some issue in your microcode, or some researcher finds security bugs in your microcode and then you want to patch them. So inside the CPU, there is a second area that is the microcode RAM that holds patchable area for microcode operations, so that you can actually write patches to microcode and execute them instead of the original microcode. But we miss a bit here, and this is how do we know that we have a patch for that microcode address? So there is a component that we can call the match and patch, that every time you're about to execute a micro instruction at the particular address, it will redirect the execution to the RAM if there is any available patch for that address. So we can start to look at the microcode, and we can see that every instructions in the microcode is coupled in a triad with 4 microoperations and a sequence word. Now the fourth one here is not shown, the fourth microoperation, since it's always an op. So for simplicity, we just don't show them. The micro instruction will usually implement some sort of functionality, for example, executing the arithmetic instruction, comparisons, while the sequence word will usually tell what is the next triad to execute, but also will usually have some sort of synchronization primitives. Think about if you're executing, I don't know, an elf-fence instructions that requires synchronization inside the CPU. And we can use the disassembler from the reverse engineer microcode format to look at the disassembly of microcode operations. So we can look at them, and we can see simple instructions. As I was telling you, this is a restricted instruction set architecture with comparison, arithmetic operands. And in blue, we have the sequence word that, for example, have synchronization primitives and tell you what is the next triad to be executed. From the microcode, you will have access to a few registers that are way more than what you would expect. You will have access to the architectural one, that are the registers that are in the x86 level, the register we all know. But you also have temporary registers that map for temporary computations. For example, for temporary values that you don't want for the architecture to know and to observe. You also have remappable registers that can be aliased to any other register that is temporary. You even have flags that are per register instead of a single flags register. So every operation will access the flag register of the inputs and write the flags to the output registers. You will also have instruction-dependent registers and even 2 instruction pointers for saving and restoring, for example, for curling microcode routines. So it's a very complex view of the registers. But the memory is not simpler. You will have different memory areas that you can access from microcode. You will have, the first one that is the physical memory. That's the memory that we all know about, that you either are able to access it virtually or even physically, just bypassing the page table. You also have internal buffers that are either shared between the CPU cores or even not shared and private to the core. So if we look at the microcode, we see that there is a ton of complexity, just by the design, but also due to the fact that the microcode is limited in size. So when you build a microcode patch as a silicon vendor, or when you even have the microcode ROM, you have to optimize the code as much as possible with respect to performance, but most importantly, with respect to the size. So the code will be extremely tangled with, for example, basic blocks that are shared between different microcode routines, or crazy optimization that transforms branches into loops, and so on. So it will be very painful to work at the microcode level. I don't know who develops that. It must be a crazy guy, tied to a wall and cannot access anything else than microcode. But I don't like to work like this. I'm a lazy guy. I want to see something better. So my first contribution has been to develop a microcode decompiler that is able to map the low-level representation of the microcode to a high-level representation. Obviously, as every time you want to automatize some work, it took 1 month to do something that I could have done in a week if I'd done them manually. But anyways, so with the microcode decompiler, we have a much better life into reverse engineering the microcode internals with a very high-level view on what is happening in the CPU, with much more simplified operations and logic. So what we did with the microcode decompiler is to understand how the CPU uses its internal components. And the most important internal components that we wanted to understand is the control register bus. So the CPU controls most of its internal units, for example, the configuration of its internal units, through the control register bus or the CR bus. So for example, any model-specific, or actually most of the model-specific registers will be actually mapped to addresses inside the control register bus. Or even like control and status registers at the x86 level, at the microcode level will just be addresses in the control register bus. System management mode configuration will be addresses in the control register bus. And system management mode is like the deepest state of the CPU that is supposed to be protected against the kernel and the hypervisor, and no one is supposed to access. And then there is a very interesting thing. That is, the LDAT is mapped into the control register bus. And the LDAT is a fundamental component for Intel CPUs that is made for post-silicon validation features. Meaning that, for example, a vendor that publishes a CPU needs a way to test it after being published. So it will use the LDAT to query the functionality and even fully access the internal components of the CPU to test for their functionality and like for performance guarantees, security guarantees. So the LDAT has full access to most of the internal components of the CPU. So now we can like try to understand where we are going. And we want to access one of the most internal components, most important internal components, that is the microcode sequencer. That is the component that controls the microcode inside the CPU. So the microcode sequencer can be accessed by the LDAT for post-silicon validation. And we said that the LDAT has access to the control register bus. So if we access the control register bus, then it means that we can access the LDAT and then the microcode sequencer. So from the control register bus, we can have full control of the microcode inside the CPU. So enter now the undocumented instructions that I briefly mentioned at the beginning. And they are very interesting since they can access the internal components in the CPU. And among them, they can access the control register bus. So we can just define simple wrappers that use those undocumented instructions in read unlocked CPUs that let us write to the control register bus. So that literally let us program the CPU just from the software level. And then we can use our reverse engineering framework to observe the patterns that the CPU uses to access that buffer, and then like just try to replicate them. So just by observing the patterns, we can like develop wrappers over our wrappers that let us write to the microcode sequencer from the software level, so that we can define operation to write the microcode in the microcode RAM, to write and modify sequence words, or even to program the match and patch to hook different operations. And if you were wondering, okay, but how do we program the match and patch? We can just still use our reverse engineering framework to observe how the CPU does that and just emulate that. So just repeat what the CPU is doing, and then just literally define the simple mathematical operations that let you write the control register bus. So you got the idea of custom processing unit. We can leverage undocumented instructions to patch the microcode just via software. This allows to completely observe the CPU behavior, since we have full access to the internal components of the CPU, but even completely control our CPUs, all via like a BIOS or a kernel module, so all via software. So with our framework, we are able to patch the microcode, hook the microcode execution, and even, not just getting a little bit smarter, fully trace the microcode execution at runtime. So with microcode patches, I told you that we can change the CPU behavior. And what does this really mean is that we can change the behavior of microcoded instructions. And for example, we can even add functionalities to the CPU. So what's the best way to introduce microcode patches if not showing you the microcode patch hello world? So we can change instruction behavior so that when you execute the instruction, instead of doing the semantic functionality that this instruction was supposed to do, you just return hello world. And which better instruction should we choose if not rdurand, which is supposed to give you a cryptographically secure random number. So let's just piss off some cryptographer and make rdurand return hello world instead of a cryptographically secure random number. So we can use our framework. Yes, we wrote a microcode assembler, so we can use our framework to transform the textual representation of our patch to the sequence of commands that you need to program the control register bus, and then to talk with the LDAT to execute and to install the novel microcode patch that we want. Then set up the match and patch to hook the rdurand instruction so that the next time you will execute rdurand, you have hello world. So here, we have a very simple program that just executes rdurand. So if you execute it, you will have random number. No surprises here. But then we have our patch that transforms rdurand to give an hello world, so that we can use our framework to install the patch. And then the next time you will execute rdurand, well, you guess it, you will have hello world. But now, I mean, we can be a little bit like smarter and do something more cool. So what if we make rdurand a little less boring? Okay, hello world was cool, but let's do something cooler. We can use rdurand and change its microcode instructions to execute and then dump system management mode memory. So system management mode is the deepest state of the CPU that no one is supposed to access. So what if we just return those data from the CPU level? But if we do that from the microcode patch, and then we just change the rdurand instruction to just access the physical address of system management mode memory, you will just get a bunch of -1s. Since, okay, you are executing from the microcode, but you're not special. But we are special, actually, since we access to the CR bus. So we can just program the CR bus for a moment to disable the protections for system management mode memory. Obviously, we have to save and restore the system management mode and mode protection memory. Otherwise, the CPU would yell at us since we are just disabling one of the most important security features. But then we can just execute rdurand and dump system management mode memory. So you either have two options. You either take one of the 200 bugs that binarly finds every year to dump system management mode memory, or you can just like change the microcode to dump system management mode memory. So here, we will have another very simple program that executes rdurand in a loop. So if you execute it, still no surprises, you have a bunch of random numbers. But then we have our magic patch that transforms rdurand, so that if you execute the patch and then re-execute the program that does rdurand in a loop, then you will have system management mode memory. And you can recognize that from the system management mode header that starts the system management mode memory. Okay, we did like cool tricks with the CPU. We found like, okay, we can change CPU behavior like as you wish. But what if we can make something even cooler and add an important security feature from the ARM world architecture and port it to x86? So let's enter pointer authentication codes. Okay, pointer authentication codes are an ARM mitigation that protects pointers from corruption signed in them, like using cryptographic signatures. So you have like a couple of instructions. For example, a pack instruction that signs a pointer using a secret key inside the CPU and a salt, so that from the original pointer, you will have a signed pointer that you are not able to use. If you would use that, you will just like crash since the pointer is now invalid. And you have the companion operation that does the authentication. So it gets a signed pointer input and authenticates the signature. And if the signature is correct, then you will get back the original pointer that you can then use. And if the signature is wrong, for example, if an attacker was able to, I don't know, modify the pointer to make an exploit, the signature will not match anymore, and then you will just have a pointer corrupted that you cannot use. So what if we now make pack just an x86 mitigation? So we can introduce like or change two instructions to implement the pack functionality. So for example, we can choose a var_w and var instructions to sign and authenticate, porting a very important security feature from the ARM world to the x86 world, borrowing that basically. So I'm aware that you don't read anything there, but it was only to show that, okay, pack implementation fits in a slide if you cheat enough to zoom it out. But we fully implemented pack with like single round of cpash, which is a very fast keyed hash algorithm, where we store the secret keys in the internal CPU buffers of the CPU, so that architecturally you're not like allowed to access them, and only the pack instructions can access them. And we implemented pack so that in like 50 microoperations, in about 20 cycles, you are able to sign and authenticate pointers. That is a feature that was supposed to be in the ARM architecture world, but now is in the x86 world. But okay, we are at OffensiveCon, so okay, it's cool to introduce new features, but we are supposed to attack them, right? So what if now we have an implementation for pack what if now we attack our implementation and try to break the security mitigation that we just introduced? So let's enter the Pacman attack, where the idea is very clever. We can borrow ideas from it. And the idea basically is that you can brute force pointer identification codes using speculative execution. So you can use, for example, gadgets in the program to speculatively execute authentication operations that are followed by a load, for example. And then if, for example, your signature was correct, then the correct address will be loaded. But if you were using a wrong signature, then you wouldn't have that signal. So you can use this as a side channel to brute force the PAC value. And when you get your address accessed, you know that the PAC value is correct, and you successfully bypassed PAC. Okay, if we implement that in our x86 Pacman, it doesn't work. So what's the issue here? We literally ported an implementation from the ARM world to the x86 world. So it must not be a design issue for our attack. And it actually turns out to be an implementation issue. Since the CPU we are testing on that is read unlocked, it's actually a Atom CPU, which is a very small CPU. And thus, the microinstructions that we implemented PAC with just fill the whole speculative window. So you're not able to access speculative memory, and then you're not able to observe the signal. So what can we do? For the purpose of our attack, we can attack a weaker version of PAC, where the design is literally the same, but you have like fewer micro operations, so that our attack now works, and you can brute force PAC signatures in just a matter of seconds. So here, we have another simple program that contains a PAC gadget that allows you to leak PAC signatures. And if we implement PAC in a matter of seconds, we can brute force a valid signature for a pointer for a feature that we just ported to the x86 world. Yeah, that was way quicker than I was remembering. So now, okay, we have beaten the feature that we just introduced. But we are way more powerful than the average guy here, since we have full control of the CPU. So why not also, instead of just porting an ARM mitigation, why just we not port a better version of an ARM mitigation? And why not implementing mitigations against Pacman? So an idea would be to introduce speculation barriers to the PAC operations so that you are not able anymore to use speculative execution through those operations. However, this would be like a too much high overhead that wouldn't make sense to just stop speculation in the processor. And it would also only offer partial protection, since you would still be able to execute like speculative gadget that authenticate in a non-speculative branch, let's say that. So what can we do? We can make a better PAC version where we make the authentication operation just fault with an invalid PAC. And then we can always remove the signature so that through speculation, you're not seeing the side channel that was allowing you to just brute force PAC. And I'm not showing you that the attack doesn't work, just trust me, it doesn't work. So now we had a feature that was like highly improving the security of our CPUs. But now let me show you just a feature that does improve security. So maybe it's out of scope for this conference, but I think it's very interesting since it allows us to make some very important operation much faster than they were like supposed to be. So let's think about debuggers. If you want to debug a program, you will execute like software breakpoints. And what is the journey of a software breakpoint? When you, with your debugger, you set the breakpoint for a program, then the debugger, what he will do, he will change the memory of that program, and he will execute an entry instruction, and will put an entry instruction at the place of the breakpoint, so that when the program will like hit that breakpoint, it will trigger an interrupt that sends a seek trap to the operating system and moves the execution to the operating system interrupt handler that we want to deliver a signal to the original process. But since the original process is being debugged, then the operating system scheduler will context switch to the debugger, then will execute the debugging functionality, like the breakpoint, that will context switch back to the operating system scheduler to resume the original process through the operating system interrupt handler that finally returns to the original process, which is very long. So what if I tell you that we can remove all of this and just change the semantics of the interrupt tree instruction to just implement the breakpoint logic at the microcode level? So first of all, we can avoid the interrupt overhead, so that we have just by avoiding the interrupt cost, we have a 50 times X speed up on software breakpoints, but also avoiding the context switch overhead. We are 1,000 times faster in executing software breakpoints in just 10 cycles. Obviously, this is not as generic as software breakpoints, but for very specific cases, this works really well. And one of those specific cases is why not implementing the coverage collection of fuzzing that, for example, binary fuzzing that uses breakpoints directly at the microcode level. So we can just introduce a patch to the entry instruction that changes the functionality of the entry instruction. Instead of triggering a software breakpoint, just takes the coverage map of the program under test, updates that with a hash of the program counter, and just increments it. Then continuing execution, and in just 10 cycles, we are able to dramatically improve the coverage collection for binary fuzzers. We saw how we can improve security, how can improve performance, and the next case studies will show you how can you improve security and performance in a single way. So let's talk about constant time division. And the issue is that division's operation latency highly depends on the input data where the division is working on. So for example, for constant time algorithm, this is a huge problem since you are not supposed to leak any information about the secret data. So if you do a division operation of some secret data, then it may happen that side channel attacks can infer that input data. So for example, stupid example, if you do 2 divided by 1, you will have 22 cycles. But if you do a very big number divided by 1, you will have twice as much, just having a much higher overhead on that. So an attacker can just observe what is the data that is looking like that the cryptographic algorithm is computing on. And now, okay, there exists a few implementations for this. So there are software wrappers that implement the division operation in a constant time way. However, these have a huge overhead, bringing this to 700 cycles. But most importantly, they need a compilation pass to transform the division operation to just calls to that software routine, or just binary patching if you're not able to recompile your binary. So maybe you already guessed what we are going to do. We can patch the division instruction to be constant time at the microcode level. This allows to have a highly reduced overhead than the original implementation, but most importantly, this is transparent to the running program, so that we can literally, without changing the running program, flip a bit in the CPU, and then make our cryptographic program secure against side channel attacks for, in this case, division operations. So I think you have enough of microcode patches. Let's talk about microcode hooks. And the idea here is that we can install hooks in the microcode to observe CPU event. So that, for example, we can set up the match and patch to trigger microcode routines that we decide at some events that is happening inside the CPU, and then just resuming execution. So for example, with microcode hooks, we can implement our own performance counters if we want to observe something that Intel didn't decide that we could observe. We can just introduce a novel performance counter as we wish to observe CPU events. So in this case, the example is, let's measure the number of time a particular instruction is executed, like var_w, that is often used by Intel for implementing security mitigations. So if you want to assess, okay, what's the overhead of that mitigation, what is the number of time that instruction is being executed, but you don't have a performance counter for that, well, you just, in 4 lines of microcode patch, you implement increment counter operation that updates a counter every time that instruction is executed. And thus you have a performance counter for the event that you want to observe. Okay, but with microcode hooks, we can be a little bit smarter. So what if we install a microcode hook that instead of just doing incremental counters or just doing operations, just dumps the timestamp at which that microcode hook has been executed, and then just resumes the operation? And what if we install that hook to all the micro operations addresses that are at the microcode level? Then we will have the timestamps at which each microinstruction gets executed. And just by reordering them, we have a full trace of the micro operations executed inside the CPU. So having a full runtime trace of what is happening inside the CPU. What can we do with static and dynamic analysis if not reverse engineering the algorithm Intel wanted to be secret? So we can trigger microcode updates, do a runtime trace of that, and use our static analysis framework to observe what are the instructions executed, micro-operations executing during the update algorithm. The update algorithm is a fundamental algorithm inside the CPU. So only Intel is supposed to be able to patch our CPUs. I mean, not anymore, but in theory, only Intel is supposed to be able to patch our CPUs, introducing like novel security features. So micro updates are both encrypted for secrecy. Maybe Intel doesn't want to disclose like some patches that it's doing, but also for security, since the microcode update is signed from Intel, and only Intel is supposed to be able to load that microcode update. So if we find a bug in that algorithm, that will be a huge break of the Intel security model of our CPUs. So what we did is to fully reverse engineer the algorithm and fully document it. So the algorithm starts with a write MSR that triggers the microcode update with the input you're giving. The write MSR, the first thing it does, apart from like very basic checks, is to move the original microcode update patch to a secure memory area on a fixed physical address. So the microcode update patch, after reverse engineering, is composed with like a few bunch of sections with an initial metadata section where you have, for example, the CPU ID where the microcode is supposed to be applied on, or the security version number to avoid downgrading the microcode update. You have, for example, a public key for the signature with the modules and the exponents, the signature itself, and then the microcode. And the first thing it does is to check that the modules and the exponents are actually the one that the microcode update algorithm expects. So then it proceeds to use a cryptographic nonce embedded in the algorithm to generate like a decryption key. That key is composed with the combination under SHA with a key expansion algorithm of both a nonce and a CPU secret that is actually a secret key inside the CPU level that you are not able to observe, and thus providing secrecy to the algorithm. Obviously, we dump that. And then the algorithm continues to generate the RC4 key, like discards the first 512 bytes to reduce the bias, and finally decrypts the microcode update. But it's not finished. It will compute the SHA-256 of the microcode patch, the nonce and the metadata of the algorithm, and then check that the signature is actually valid. And if it goes with a correct check, then you finally can parse the microcode update. So what we did is to assess what is the attack surface of the algorithm. So we didn't find very big vulnerabilities in the algorithm, but I think it's very important to publicly assess what are the security features of the algorithm and what are the attack surface that could go wrong or very wrong. And the first of all is, as you may notice, the microcode update algorithm uses RC4, which is not the best encryption and decryption algorithm in the world, but is, I would say, kinda used securely. The key for RC4 is generated with a 16-byte secret key, like I would say combined with a 32-byte nonce that is unique per update, and then expanded under SHA to a 256 bytes key that is pretty strong for RC4. It even discards the first bytes to reduce the bias of the microcode update decryption routine. And then if we check for the attacks against RC4, we find that you need millions of encryptions or decryption, and we only have 500 updates, so the attack against RC4 are not really feasible here. But if you find millions of microcode updates, let me know, so we can try. And then we move to see, are they using RSA correctly? So RSA keys, for example, the public key and the exponents, are dark-coded, so that you cannot use like another key or like try to trick that, you putting, I don't know, the exponent to 1 with these nice tricks against RSA signatures. But this also means that if you break those keys, then you fully break the signature. However, those keys are 256 bits with secure paddings on the signature, so it's pretty hard to break them, unless you are like NSA, I don't know. Anyone? Okay. And then what the key signature is doing, it will check all the important metadata that we cannot then corrupt. For example, it checks the security revision number. So you cannot take a micro-update algorithm and change the security revision to, for example, downgrade the CPU security, which is nice. I mean, nice from them, not for us. You can check also the CPU ID values where the micro-update is supposed to be applied on, so you cannot install, for example, a faulty micro-update on another CPU. It also checks the nonce, so we cannot mess with the decryption key. And then it checks, obviously, the decrypted update to check that you didn't change bytes in the update. So very sad, we move to see, okay, what are the other features in the update that may have vulnerabilities? And I told you, like initially, that one of the first things that the micro-update algorithm is doing is to move the micro.patch to a secure memory area. And this secure memory area is this temporary physical address where the micro is decrypted. So there is a physical address inside the CPU that is used as secure memory. So we have a nice operating system. So let's ask Linux, hey, do you know this physical address? But this is fully undocumented. So while this is mapped, like at the Linux level, existing in the maps, in the memory, like IOMEM, Linux does not know knows nothing about this address. And if we try to read the physical address just by dumping it, we have a bunch of Fs, which really doesn't make sense. So you're not faulting, but you're having data which is fixed, invalid. So what is happening here? It's similar to, for example, if you would read enclave memory or system management mode memory, you will get a bunch of Fs. So there is something strange definitely on this algorithm. But we have complete microcontrol, so we can check what the CPU is doing with this address. And what we can do is that we can reverse engineer the micro-update algorithm to see how the CPU uses it. And we see that this address is dynamically enabled by the CPU. So it's like there is some switch internally that makes this address valid or like returning a bunch of Fs. So we can enable it and I would say poke it. So if we try to access it, we see that this address is surprisingly fast. It's about 20 cycles of being accessed, which is very fast for a memory mapped IO region. So it's kind of strange. What is also strange, if you access this buffer from a core, and then you write some data, and then you access the same buffer, same physical address from a different core, you will see different data, which doesn't make sense if you think about it, since it's the same physical address. So what is happening here? We also find that the actual memory behind this physical address is limited in capacity, which also doesn't make sense, since the physical address is a very big region, and you can only fit like 64 to 256 kilobytes of valid data. And if you fit more, then you start to see a replacement policy on the data that you're seeing. So what is happening here? We have some kind of strange behavior that really resembles a cache, I would say. So our hypothesis, which is, I mean, not confirmed, but that's my hypothesis, is that this is a special view that the CPU has on the L2 cache, which fits with the access time, with the fact that the context is not shared, with the fact that you can only fit a limited amount of data, and with the replacement policy that looks like a cache replacement policy. So obviously, now we know about this physical address. So what do we want to do? We want to exploit it. So we can try to exploit with race conditions, for example. So the idea is to corrupt the microcode after that's been decrypted and the signature has been checked, but before it is being applied. However, this is like not feasible to do, since, as I told you, each core has a private area. This is not shared. And then you may think, okay, we can use maybe hyperthreading to like kill the memory while we are updating the algorithm. But the fact that the trigger of the micro update is a write MSR disables the hyperthreading. So we are not able to execute something in parallel to corrupt that memory. And also, since this is dynamically enabled and disabled, then if you try to dump it just after a micro update, then that will be disabled and you just will dump a bunch of Fs, as I showed you. But we can try to like have some smarter attacks. What if we move to architectural attacks? So what if we do some kind of attack like the memory sinkhole, which is a very interesting attack proposed by Christopher Thomas in a Black Hat session, where the idea is, okay, you have a victim memory area that you want to exploit somehow, and then you have a very nice buffer inside the CPU memory address space, which is the epic MMIO region. So the epic MMIO region is an area that is supposed to let the CPU control the interrupts that it has. For example, letting the timer interrupts being configured and similar functionalities. But the nice thing of this memory area is that this is a configuration inside the CPU where you can literally move the area over the shadow others that you want. So we can move the epic MMIO region over the secure memory area, so that during a macro update algorithm, the CPU will want to access the secure memory area, but actually it will not access the security memory area. So it will just access the epic MMIO region. So this is a very nice attack, and it works, but it has some issues. So the epic MMIO region is a very restricted area, and there's a lot of rules on how you can access that. So for example, on some CPUs, this is like the behavior varies on like per CPU, I would say. So on some CPU, if you do that, you will be able, for example, to leak a few bytes of data that are being writable in the MMIO region, and that the CPU will just write on that, thinking it's secure memory, so you will be able to leak a few bytes of the macro update algorithm. However, on most CPUs, what happens is that the CPU will just triple fault and die, basically, since it's using a very important memory area, kind of wrongly, like doing decryptions on that, which doesn't make sense for the epic MMIO region. So what is happening is that, in the end, while this attack could have worked if the epic MMIO region was programmed, I would say, differently, this doesn't work a lot. Why don't we move to micro-architectural attacks then? We tried like architectural ones, we tried race conditions. So can we transiently leak micro updates? So for example, we can use attacks like fallout or micro-architectural data sampling that lets you sample data that is in flight in the CPU. However, you have to actually be able to sample the data. So the fact that you don't have hyperthreading enabled, like the effect is that if you do that, your sampling will be either before or after the macro update algorithm. So the data that you will sample will be completely unrelated to the macro update, even on CPUs that are vulnerable to this kind of attacks. We can try to do an attack like foreshadow L1TF that leaks the content of the L1 cache. So if the macro update would be using the L1 cache, then we will be able to leak that content. However, it doesn't seem, at least for our experiments, that the macro update is using that buffer. So the memory that we leak with that kind of attacks is just unrelated to the macro update. We also tried an inverse epic leak attack, which is a very interesting attack. Basically, epic leak is a vulnerability that I discovered, actually, but it's a vulnerability that lets you sample data from the superqueue inside the CPU. So what's happening is that every data that passes through memory will be in the superqueue. So what if we like do an inverse epic leak attack and make the macro update algorithm sample data by itself, since it's using the L2 cache, which is very near the superqueue? What if we make that attack overshadowing the epic MMIO region over the secure area, and thus the epic MMIO region would leak data on epic leak vulnerable CPUs from the data that we injected? So we make the macro update use our data instead of the secure memory data. This is very sad. You had a spoiler there, I didn't remember. However, the internal buffers are flushed before the macro update with an operation which is a kind of write back invalidate. So you will not have your data that you want to inject in the macro update in those buffers, which is really sad. So okay, this is just a preliminary idea. I may go to the booth for fault injection attacks like in the other area. So what if, like, when everything fails, you go to fault injection attacks, right? So what if we can induce faults and skip, for example, checks inside the microcode level? So to my view, like for my reverse engineering, so this may be wrong, but we didn't find any real fault injection protection inside the algorithm. So you could make a fault injection attack that lets you skip the signature operation checks, since they would be the most profitable ones. But however, the micro update is not persistent. So this would be a kind of attack where you need basically your CPU always being under a laser to do that same attack every time you boot the CPU, which is not the best thing for usability, but would be very interesting to explore this direction more. So after failing to break the algorithm, we still continue the reverse engineering effort to understand, okay, what is the structure of microcode update? Can we understand more of the microcode updates? So we went to parsing the decrypted microcode updates for Goldmont CPUs. And with our, I would say, big surprise, we found that a microcode update is actually a bytecode. So what I was expecting was to find, I don't know, some flash data that you just, some data that you just flash to the CPU and put on the match and patch and microcode RAM. But what we found is that the microcode update is actually a bytecode that tells the CPU how to update itself. So it will contain a bunch of commands that, for example, can reset the internal states inside the CPU, can write microcode values, or can hook different operations multiple times during the update to do, for example, temporary updates while updating the whole CPU, or writing to internal commands, to internal buffers, sending commands to the CR bus, so changing the configuration on the fly while updating. And it has even control flow directives to do, for example, branches inside the microcode update, which actually makes the microcode update a Turing-complete language, which is incredibly surprising, I would say. So what we did, we created a parser for microcode update and collected all the microcode updates that exist for Goldmont CPUs. So we decrypted all of them and published them so that the security community can study and understand them better. So to conclude, with custom processing unit, I hope at least, we massively deepen the understanding of the internals of modern CPUs. We developed a static and dynamic analysis framework that allows you to, for example, customize, observe, and even trace microcode execution at runtime. Our framework includes a decompiler for microcode, an assembler that lets you write patches, a patcher that lets you apply those patches, and a tracer to observe fully at runtime the microcode execution that allows us to completely control our CPUs. Our framework is open source, so you can play with that if you have a read and lock CPUs like a Goldmont one. So thank you very much. If you have questions, I will be happy to take them. I don't know if you need a microphone.
Hi.
Oh, okay.
Nice talk.
Thank you.
As I understand, the patching of microcode at runtime requires read and lock. Because at the beginning you mentioned you don't need hardware debuggers, but to enter unlock you need the debugger.
Yes.
Okay, thank you.
Oh, okay. So the issue is that you need access to those undocumented instructions that have access to the internal buffers, and you can activate those undocumented instructions only with read and lock CPUs. Otherwise, they will not, they will just be NOPs. So, for example, if we were able to break the microcode update algorithm, or someone of you is able to break it after we fully documented it, then it would be very nice, since you basically break the security guarantees of that, and then you would achieve a kind of a read and lock on all the CPUs that share the same microcode update algorithm. Oh, okay, okay. So are you going away, or do we have a question? Okay. So if you don't have any further questions, I will be around and at the parties tonight. See you around then.